I'm Anil Kumar sharing with you a video on derivatives of logarithmic functions. This is mainly for students who are just beginning to learn how to find derivative of logarithmic functions. We'll explain the concepts in the first part and then we'll have 10 questions for practice. Some of them will be multiple choice questions. Now before we begin, let me write down what you should know, right? So first you should know that if a function is y equals to ln x, in that case the derivative of this function is 1 over x. Okay, so this is what we did when we introduced you to exponential functions. So there ln is the natural log to the base e, right? Now, and also you should know how to write log in a different base. For example, if I give you log b of x, we can change the base, and change of base formula is, if I want to change it to a, then we could write this as log of a of x over log of a of b, right? Now this is very important formula for us. We could change this base to e also, and then write this formula as ln x over ln b. So we are going to use these two formulas to start with and find derivatives of these three functions. We need to differentiate each one of them. First one here is y equals to x squared ln x. You know derivative of ln x is 1 over x. These are two functions. We'll apply the product rule, right? So if I apply product rule, I can do this derivative. So I could write derivative of this function as dy dx, differentiating with respect to x on both sides. We have dy dx equals to, so product rule means derivative of the first function, so d dx of x squared times ln x plus the first function times derivative of the second function, right? So d dx of ln x, correct? So let me do part A here. So I'll write A here, and that's my portion A. Then we'll do B and C separately. Okay, so the derivative is very clear. X squared is 2x, and we'll just write ln x plus x squared times derivative of ln x is 1 over x, right? So we'll times this by 1 over x, and that gives you, they cancel away, and so you get 2x ln x plus x as your result, right? You can always take x common and write this as we could take x common and we'll write this as 2 ln x plus 1. So that becomes the derivative of the first function, correct? Now let us see how to find derivative of a to the power of x. Now let's do b, which is we need to find derivative of y equals to a to the power of x. Now for such functions, we'll derive a formula here, and in following videos, we'll use that particular formula. So the idea here is to take natural log on both the sides. So we can write this as ln y equals to ln a to the power of x, right? Which could be written as ln y equals to x times ln a. Now a is a constant in this particular case, correct? A is a constant. So let's do it on the right side. I'm just saving on space. Now if we differentiate with respect to x on both sides, so we'll do differentiate with respect to x, this function, what do you get? Derivative of ln y will be 1 over y, so we get 1 over y dy dx, correct? Equals to, here ln a is a constant, so we really get just ln a here, so we get ln a. So we get the derivative dy dx as dy dx as y times ln a. Do you see? So if it is y equals to a to the power of x, then the derivative is y times ln a. So that is a new derivative which we have learned. So if we want to find derivative of, if I have y equals to a to the power of x, in that case the derivative is, now y in this case is a to the power of x. So we could write this as a to the power of x times ln a, correct? So I could always write this as a to the power of x ln a. Does it make sense to you? Correct? So that is the next formula which we have derived, and we are going to use this formula extensively in all our examples. Okay. Next one here is finding derivative for log to the base bx. So let me rewrite c as y equals to log to the base b of x. Now I'll change this to ln. So I'll say this is ln x over ln b, right? Now b is a constant, correct? B is a constant, any real number. So that becomes my expression now. So basically we want to find derivative of ln x divided by a constant, which is ln b, right? So clearly this derivative y dash will be, derivative of ln x is 1 over x. So we get 1 over x times, you can say, ln b. Is it okay? So this becomes the formula for the derivative of log to the base bx. Is it okay? So if you get an expression where y equals to log bx, in that case, you know y dash is 1 over b times ln, 1 over x times x, 1 over x times ln b. Is it okay? So that is your formula, correct? So these are the formulas which we are going to use and solve rest of the questions. So let's move forward and take few examples. The very first question is a multiple choice question which says slope of tangent line y equals to log to the base 2x at 2, 1 is what? Now that is how a logarithmic function will look like, right? So this is our log to the base 2x function. We are trying to find the slope of this function at x equals to 2. So somewhere here, right? This is what we are trying to find. Slope of this tangent line. As you can see, logarithmic functions have a domain where x is greater than 0, right? So that's the domain for such logarithmic functions. Now we can apply the formula directly here. So I hope you remember the formula. If we have y equals to log to the base b of x, then the derivative is 1 over x times ln b, correct? So that's the formula. If you apply this, you get your result. So we are looking for x, 1 over x times ln b, and b is 2. So and at 2. So we get derivative of this function as 1 over x times 1 over ln 2, right? Now since we have to find derivative at x equals to 2, I'm replacing this by 2, right? So the derivative at x equals to 2 will be 1 over 2 times 1 over ln 2, right? Now we don't have this option here, but we can apply the properties of logarithms and write this as 1 over ln 2 square, which is 1 over ln 4, correct? So that is our answer. So the answer is option B. So I hope that is clear. It's kind of tricky. It's a very important first question which you might see in your test paper. Okay. The next question here is question number 2. Slope of tangent line y equals to 5th root of ln x at the point is 2, 1. Now let's find the derivative. So we are writing y equals to ln x and the power is 1/5, correct? So we'll apply the power rule first. So it is 1 over 5 ln x to the power of 1 over 5 minus 1, so that gives me minus 4 over 5, correct? Times derivative of ln x, right? So that gives us 1 over 5. Since all of them are written like this, I'm writing this as fifth root ln to the power of 4. Perfect. And the derivative of ln x is 1 over x. So what you get here is 1 over 5x and the fifth root of ln x to the power of 4. So the answer which matches is option C. So I hope it is well understood, it's clear. Now onwards, I'd like you to pause the video, copy these questions and solve. Question number 3. Equation of tangent line to y equals to log to the base 2x at 8, 3 is one of these. Now we will use the formula y equals to mx plus b to find equation of tangent line, and slope m is basically the derivative, right, at x equals to 8 in this case, right? That is the strategy. So let's find the derivative of the function. We are given y equals to log to the base 2 of x. The derivative will be 1 over x times 1 over ln 2, the base. To find this derivative at x equals to 8, we will replace x with 8, so we get 1 over 8 times 1 over ln 2. So that becomes the slope. Now, using this equation, y equals to mx plus b, we'll find the y-intercept b. So we could write this as y equals to slope of 1 over 8 times 1 over ln 2 times x plus b as our equation. Now, replacing y with 3 and x with 8, we get 3 equals to 1 over 8 times 1 over ln 2 times 8 plus b. So as you can see, 8 and 8 will cancel. So the y-intercept will be 3 minus 1 over ln 2, right? So that is the y-intercept. And so the equation is the slope 1 over 8 times 1 over ln 2x, and the b value is plus 3 minus 1 over ln 2. So which one does it match with? So minus. So this is the one which matches. Correct? So let's move forward and do some more practice questions. Question number 4 here is, find the derivative of y equals to log to the base 5 of 3x plus 2 to the power of 4. Correct? So we'll write derivative of this function will be 1 over the function itself, which is 3x plus 2 to the power of 4, correct, times 1 over ln 5 times derivative of inside function, correct? So we'll say d dx of inside function, which is 3x plus 2 to the power of 4. Perfect. So this could be written as all this, which is 1 over ln 5 within brackets 3x plus 2 to the power of 4 times, we'll apply the power rule here, which is 4 times 3x plus 2 to the power of 3, and derivative of inside function will do times 3. Perfect. So we get 4 times 3 as 12 over, so if you see this, 3 powers cancel out, so we are left with just 1 power of 3x plus 2 in the denominator. So we have ln 5 times 3x plus 2. So that matches with the last option, option D. So I hope it's absolutely clear, right? Question number 5 here is, find equation of tangent line to the curve y equals to ln x at e equals to 0, right? So the function is interesting, y equals to ln of ln x, correct? So the derivative y dash will be, derivative of ln x is 1 over this thing, which is ln x, times derivative of inside function, which is ln x, correct? So that gives you the value as 1 over ln x times derivative of ln x is 1 over x. Correct? So that becomes the derivative. Now let's find this derivative at the point e0. So the derivative at x equals to e will be 1 over ln e times 1 over e. Now 1 over ln e is just 1, so we get 1 over e as the derivative, correct? Or the slope. So that is the slope of our line, correct? Now we need to find the equation of line, which is y equals to mx plus b. The point is e0. Substituting 0 for y, basically, right? So that is 0 for y. Slope at e, we have already found as 1 over e. So this is 1 over e. The value of x is e. So we'll replace x with e plus b. So that gives us the y-intercept as minus 1, right? Minus 1 is b. So we get our equation as y equals to slope, which is 1 over e, x, and b is minus 1. So this is the slope which we get. Now we have written it in a kind of standard form, so I'll bring all the terms together. So if I multiply by e, what do I get? I get ey equals to x minus 1. Bringing it to that side gives me, and 1 on the other side, we get x minus ey equals to 1, correct? So that is our answer, x minus ey equals to 1. Option D is the right option for us. I'd like you to go through this once again, see the calculations, correct? I hope it helps to understand how we found that equation. Now question number 6 is find derivative of y equals to x to the power of x. Now this is a very important question at this stage. How do you find derivative of x to the power of x? Now we are going to use logarithmic rules here. So we'll take log both sides, so ln both sides. So we get ln y equals to ln x to the power of x, or ln y equals to x times ln x. So we kind of transform our equation, right? That's the trick. Now we are going to differentiate with respect to x on both these sides. So derivative of ln y is 1 over y dash. And here we'll apply the product rule. Derivative of x is 1, so we get ln x plus x times 1 over x, right? So which basically is ln x plus 1. So we can get our derivative as equal to y times ln x plus 1, where y is x to the power of x. So x to the power of x times ln x plus 1, correct? So this is our last option, D here. That is how we'll do this particular question. Here is question number 7. You need to find derivative of the function y equals to x squared plus 1 times 2x plus 3 whole cube divided by x squared plus 5. Now we are going to use properties of logarithms to find this derivative, right? Let us see how it really helps to simplify the whole thing. We are given y equals to x squared plus 1 times 2x plus 3 whole cube divided by x squared plus 5. Now see what happens if I take natural log both sides. That is to say, if I do ln y on this side and ln of this function on the right side. Using the properties of logarithms, we could now write this as ln y equals to. Now this is like product. It could be written as ln x squared plus 1 plus ln 2x plus 3 whole cube minus ln x squared plus 5. Do you see that? Let me rewrite with 3 here. So it'll be ln x squared plus 1 plus 3 times ln 2x plus 3 minus ln x squared plus 5. So by simply using the rules of logarithms, we could actually simplify the rational function, write it as sum and difference. Now, if I do derivative on both sides with respect to x, what do I get? So on the left side, I get 1 over y dy dx. Here, the derivative of ln function is 1 over the function itself times the derivative, which is 2x, plus here we get 3 over 2x plus 3 times the derivative of this, which is 2, minus 1 over x squared plus 5 times derivative of x squared plus 5, which is 2x. Do you see that? So now we can write dy dx as equal to y times, and I can replace y with all this, correct? So instead of writing y, I'm writing the whole expression, which is x squared plus 1 times 2x plus 3 whole cube divided by x squared plus 5. So basically, I'm replacing this y, since I'm taking it here, with all this. Do you see that? The function itself. And then we have everything here inside. So we have 2x over x squared plus 1. And here we get 3 times 2 as 6 over 2x plus 3 minus we get 2x over x squared plus 5. Do you see that? So using logarithms, you can actually simplify the expression and then easily find derivatives of those functions. So I hope that really helps, right? So let's move on and take up other questions. Question number 8 here is, differentiate f of x equals to a ln 2x plus b and find domain of its derivative. So let's find domain of this function. So we have f of x as equals to a ln 2x plus b, where a and b are constants. So the derivative of this function is a over 2x plus b. So that is it. So that is the derivative of this function times the derivative of inside function d dx of 2x plus b. So I could write this as a over 2x plus b times 2, or we could write this as 2a over 2x plus b, right? So that becomes the derivative of the function, and the domain of this function is, we are writing domain of the derivative, right? So domain is, in this case, 2x plus b cannot be equal to 0, right? So here 2x plus b is not equal to 0. So we have x is not equal to minus b by 2, correct? But strictly speaking, when I'm writing domain of the derivative, I have to look at the function also, right? So if you look at the function, which is ln 2x plus b, we know 2x plus b should be greater than 0. So that means 2x should be greater than minus b, or x should be greater than minus b by 2, right? So the domain strictly will be x greater than minus b by 2. So x belongs to real numbers, where x is greater than minus b by 2 becomes the domain of the function. So I hope that is absolutely clear. Okay. We are almost at the end. 2 more questions to go. Question number 9. Differentiate 3 to the power of y equals to x squared plus 1. So we'll again apply the properties of logarithms to find the derivatives, right? So we are given the function 3 to the power of y equals to x squared plus 1. So we are going to take logarithms both sides. So we can take ln of this function equals to ln of this function, correct? So when you do this, then you get, applying the properties, we get y ln 3 equals to ln of x squared plus 1. Now differentiate both sides with respect to x. So this is a constant, right? So we get derivative of y is 1. So we get ln 3 dy dx, which is equal to 1 over x squared plus 1 times derivative of inside function, which is 2x. So dy dx is equal to 2x over, that comes in the denominator, ln 3 times x squared plus 1, correct? So that becomes the derivative of the given function. So I hope that is absolutely clear. So let's move on, and here is our last question. Question number 10 is determine maximum and minimum for y equals to x squared ln x. So I'd like you to pause the video, answer the question, and then look into my suggestions. Now in this case, to find maximum and minimum, we need to find the first derivative and analyze the second derivative. So we are given y equals to x squared ln x. So dy dx is equal to product rule. We get 2x ln x plus x squared times 1 over x. So we get dy dx, or the first derivative, as let me write as 2n ln x, and here we get plus x, correct? You can take x common. So if you take x common, then what you get here, you get 2 ln x plus 1. Now let's find the critical numbers. Critical numbers are when this derivative is 0. So this is x equals to 0 could give you a critical number. However, we have a restriction here. Let me write it in red. That when you have a function like this, x has to be greater than 0, right? Otherwise, this is not valid. So this is not valid. Correct? So the other is that 2 ln x plus 1 equals to 0. So that gives you ln x equals to minus half as your restriction, and then you can take e on both the sides. Then what do you get? Let me see what ln x equals to minus half gives you. So taking exponents on both the sides, we have e to the power of ln x equals to e to the power of minus half, right? And e to the power of ln x is x. So that means x is equals to 1 over square root e, or e to the power of minus half. So that is what you get as a critical number in this particular case. Correct? Let's analyze this critical number for maximum or minimum, right? So we have this critical number here, e to, what is the value of e to the power of minus half? So 1 divided by square root of e, which is equal to 0.6. So we can take a value which is, this is like e to the power of minus half. So on the left side, let me take a value which is 0. Let us say 2, and on the right side we can take a value which is say 1. Is it okay? So we are trying to analyze the value of our derivative, which is y dash equals to x times 2 ln x plus 1, correct? So if I substitute 0.2, what do I get? Let's do. So if I substitute 0.2 here, then we get 0.2 times, within bracket, 2 ln 0.2, right, plus 1, bracket close, equal to. So at 0.2, I get a value which is negative 0.44, correct? Now let me substitute 1 here. So we get 1 within bracket, 2 times ln 1, right, plus 1. So there is no harm calculating these values even when you know some things are obvious. Is it okay? But the important thing here is that for 0.2, that means on the left side, you get negative value. On the right side, you get a positive value. Perfect. So that clearly indicates that we have a minimum in this particular case, right? So we have a minimum. So we have a minimum at x equals to e to the power of minus half. So that is what we have. And now we can find the value of the function by substituting x equals to minus half in the expression. So we get y equals to e to the power of minus half whole square times ln e to the power of minus half, right? So that gives you, so that is e to the power of minus 1 or 1 over e. And here we get ln e is 1 to the power of minus half. That comes here in, so we get negative 1 over 2, right? So the value is negative 1 over 2e. So in this case, we have an absolute minimum. In this case, we can say a minimum now. We didn't really check for that. So minimum is at, the coordinates are e to the power of minus half and the y value is minus 1 over 2e. Perfect. Now some of you could actually find the second derivative and then check at the critical number, which is e to the power of minus half. So you could do that also. Perfect. So I didn't do that, but you could do second derivative. So this is your y value. So derivative, the derivatives, the second derivative could be derivative of this, which is 2 ln x plus 2x times 1 over x plus 1. And if I substitute the value e to the power of minus half here, what do I get? So I get 2 times e to the power of minus half gives me minus half here, plus 2x over x indeed is 2, and plus 1, correct? So that gives you plus 2 as your answer. Since the second derivative is positive 2, we are looking for concave up, right? So since second derivative is greater than 0, right? So we have concave up, and that means we have minimum. So that could be the second way of figuring out whether the critical number represents a maximum or a minimum. So I hope with this you have learned few things about how to differentiate logarithmic functions, how to find equation of a tangent line at any point on the curve, and also understand maximum minimum. You have also seen how logarithms can be applied to simplified finding derivatives. That's a huge application. So we'll have now the part 3, where we'll combine logarithmic and exponential functions with their applications. I hope you find this journey useful and interesting. Feel free to write your comments, share your views, and if you like and subscribe my videos, that'd be great. Thank you and all the best.